Welcome to SciFlux, where science meets discovery. Every day we bring you the newest breakthroughs shaping the science world. His video is all about discoveries in computer science. Let's start with a question. What if we could combine human logic with AI creativity to discover new drugs? That's the promise of symbolic neural generators, or SNGs. Neural networks can generate molecules, but they sometimes break chemistry rules. Symbolic methods are precise but limited in creativity. SNGs merge both approaches. A symbolic learner studies a few examples to define chemically valid blueprints. Then, a neural generator creates new molecules guided by these rules, producing candidates that are both innovative and valid. In early-stage drug design, SNGs performed as well as top methods on known targets and even generated promising molecules for poorly understood ones. The symbolic rules also help filter compounds ready for lab testing. By blending logic and AI, SNGs offer a faster, smarter way to explore new drugs, paving the way for the medicines of tomorrow. On another news, tracer kinetic modeling is vital in medicine, helping diagnose diseases, plan treatments, and study cancer. But it depends on the arterial input function, or AIF, which is hard to measure and often invasive. Researchers now use AI, a physics-informed CycleGAN, to solve this. This model learns from data while respecting the underlying physics of the system. Adapted for dynamic PET scans, it predicts the AIF without invasive procedures. Even better, the parameter maps it generates, showing how tracers move through the body, closely match traditional methods. This approach makes PET imaging faster, safer, and more accessible, combining AI and medical physics to improve patient care and streamline diagnosis and treatment planning. Moving forward, predicting a protein's function is a complex puzzle. Proteins carry information in their sequences, 3D structures, and interactions. But combining these data sources is challenging. Researchers developed DAMPI, diffused and aligned multi-modal protein embedding, to tackle this. First, it aligns sequences, structures, and other intrinsic data. Then, it fuses this with protein interaction networks using a condition encoder that incorporates graph-aware knowledge. The results are impressive. DAMPI outperforms or matches existing methods for protein function prediction, showing that both alignment and fusion are essential for accuracy. By reliably combining multiple data types, DAMPI provides a scalable framework for protein analysis, accelerating discoveries in biology, medicine, and biotechnology. Next news, reinforcement learning from human feedback, or RLHF, helps fine-tune large language models by learning from human preferences instead of direct rewards. But analyzing it theoretically has been challenging. Most studies rely on complex methods like Bradley-Terry models and optimistic or pessimistic estimates. This new research takes a simpler approach. The authors show that a greedy sampling strategy, using empirical data directly, can be provably efficient. The key is a structural property of the optimal policy under a KL-regularized objective, which lets the greedy method work exceptionally well across both realistic and classical preference models. The takeaway? In RLHF, simplicity can be surprisingly powerful. Greedy sampling isn't naive. It provides strong guarantees and deeper insight into how language models truly learn from human feedback. What do you think of this piece of research? Reinforcement learning has shown promise in wireless networks, but current methods are data inefficient and fail to adapt to new conditions. They learn patterns, not the underlying logic or physics of the system. To fix this, researchers created a dual mind-world model, inspired by how humans think. System 1 quickly learns network dynamics, while System 2 reasons logically for long-term planning. Instead of relying on real-world data, the model learns through imagination rollouts, simulated experiences that help it predict, plan, and act even without new observations. Tested on realistic wireless simulations, this approach greatly improves data efficiency, generalization, and adaptability, outperforming state-of-the-art RL methods. By combining fast intuition with logical reasoning, this dual mind framework brings us closer to truly intelligent wireless networks. This breakthrough is truly amazing. As 6G networks emerge, combining communication and sensing, known as Integrated Sensing and Communication, ISAC, becomes crucial. But optimizing these systems while keeping fairness among users is a tough challenge. This study proposes a dual reconfigurable intelligent surface, RIS, setup that jointly optimizes both active and passive beamforming. First, the dual RISs estimate user angles to simplify the optimization process. Then, an alternating optimization algorithm fine-tunes the transmit and reflection parameters. For the complex RIS phase shifts, a sensing-assisted approach reduces computation while maintaining accuracy. Simulations show that this design achieves performance close to the ideal continuous phase benchmark, far surpassing traditional methods and even single RIS systems. In short, dual RIS ISAC systems could be the key to smarter, fairer, and more efficient 6G networks. Another amazing work. This study introduces ReplicationBench, a new benchmark designed to test whether AI agents can reproduce entire astrophysics research papers, from equations and data analysis to code and results. Astrophysics is the perfect testing ground since it relies heavily on data and computation rather than physical experiments. Each paper is broken into key tasks, co-developed with the original authors, allowing researchers to measure both faithfulness, how closely the AI follows the original methods, and correctness, whether its results are technically accurate. The outcome? Even the most advanced AI models score below 20%, revealing major gaps in their ability to conduct rigorous scientific work. ReplicationBench sets the stage for evaluating and ultimately improving the reliability of AI in research. This study is what science is all about. In every complex system, from gene networks to decision-making processes, stability is essential. But how do these systems remain reliable under changing conditions? The answer often lies in canalization. Like a canal guiding water, some inputs dominate, steering the system toward a specific outcome and making it robust. Redundant or weaker inputs, known as degeneracy, also play a role, helping systems adapt while maintaining order. To study this, researchers used Boolean functions, simple logical rules underlying complex systems, and developed formulas to measure how often canalization occurs, especially when every variable matters and at least one dominates the outcome. The results reveal that stability isn't just luck, it's built into the logic of life itself. By quantifying this hidden order, we gain insight into how complexity remains remarkably resilient and beautifully organized. This is amazing news. Online harassment, especially targeting women, is evolving fast, from doxing to deepfakes, yet efforts to stop it remain fragmented. Police, tech companies, and researchers often speak different languages, making coordination hard. To fix this, researchers created the Gender-Aware Ontology of Online Harms, or GAO, a shared framework mapping the types of abuse, how they happen, and how to prevent them. By giving everyone a common language, GAO helps unify policies, technology, and support systems. The goal is clear: turn scattered efforts into coordinated action, building a safer, more equitable digital world for all. Finally, a study out how we communicate. Digital technologies, from the internet and social media to AI and robotics, are reshaping our world, offering huge opportunities but also serious challenges. Their path isn't fixed. It swings between freedom and control, participation and domination. A new volume brings together scholars from communication, sociology, and science and technology studies to examine these shifts across regions and domains. By analyzing power dynamics in the digital landscape, their work reveals how our digital futures are being shaped. The goal? To better understand these changes and inspire more democratic, inclusive, and preferable futures in our interconnected world. Thank you so much for watching and following our work. If you want to stay updated with the latest scientific breakthroughs, don't forget to subscribe to SciFlux and join our newsletter for daily insights straight from the front lines of research. See you next time.